Okay, hello everyone and welcome to the presentation of my master's thesis. I presented it unofficially in this department, like in Charles this morning. Okay, hello everyone and welcome to the presentation of my master's thesis. I presented it today actually in the morning and had it recorded, but in here in Charles. But you know, the recording froze after some point, so I figured we might as well do it the old-fashioned way, right? So I imagine you guys know what mine is, right? But in case you don't, okay, hello everyone and welcome to the presentation of my master's thesis. I presented it here in Charles in the morning and had it recorded, but the recording froze, so I figured I would do it the old-fashioned way with my cell phone. So hopefully we all know what a minor is, but in case we don't, let me explain it. So we all know what a subgraph is. So this guy is a subgraph of this guy. Let's say this is G and this is G prime. G is a subgraph of G prime, and why is it a subgraph? It is contained in it. That's the intuitive notion we wish to describe. So hello everyone and welcome to the presentation of my master's thesis. I presented it today unofficially in Charles, but in the noon seminar, and had it recorded, but the recording froze. So I figured I would do it the old-fashioned way with a cell phone because I want to have it recorded. So I suppose we all know what a minor is, hopefully, but in case we don't, so G prime, as you see, I guess at least we all know what a subgraph is. So G prime is a subgraph of G, and we are trying to convey the notion of containment. So someone might say, okay, look, you know, let's say we add a lot of vertices here. So this is a path now. And the idea is that somebody might say, look, okay, this path, it's like it functions like a big edge, right? So we could again say we contain this graph, and this is the notion of a topological minor. And somebody might take this a step further and say, okay, look, let's say that here, like instead of vertex, we have some kind of connected component that neighbors all vertices that G prime neighbors. Then we can treat it like a big node, right? So we just, you know, we say that this graph G contains G prime as a minor if we can find the number of nodes, a number of connected components, that if we turn into nodes that neighbor the same vertices that the connected component neighbored, we get G prime. In this case, G contains G prime as a minor. And we can, of course, still always remove a couple of vertices and edges. So, can you guys think why every planar graph is a minor of another planar graph of maximum degree 3? So no theorems are needed for this. It's very easy to see. So let there be a planar graph G. How to find a planar graph G prime that contains it as a minor and has maximum degree 3? And the idea is quite simple. We just, we just take an open disk around the vertex. We delete what's inside, and some topological caution will be needed for the edges, but let's forget about that for a minute. And then we draw no vertices where the edges intersect the disk, and then we connect all the vertices with edges in a circular fashion. The graph is still planar. All vertices are of maximum degree 3, and obviously if we collapse the red circle we will regain the initial graph. And we do this for all vertices, and in this way we get the graph of maximum degree 3. So let me write it. And that's a very basic fact. Now, in 2021, Georgakopoulos showed that every graph in form K5, so form K5 is the class of graphs without a K5 minor. Form stands for forbidden. He showed that every graph in form K5 is a minor of another graph of form K5 with maximum degree at most 22, and asked if this is smallest possible. And the answer is that, of course, 22 is a very natural number, and we can get that lower. In fact, He gave me that problem. I don't think he had looked at it that much because it was quite easy to get it down to 3. And this begs, this motivates the following definition. So let delta of C be, we want to minimize this value, right? It's time. So let delta of C be the minimum integer k such that for every g in C, there is another g prime in C with maximum degree at most k. And this is only defined for C. C is also a minor closed class. And this is a very simple parameter, elegant, and yet it is very general as well. It regards all minor closed classes. So we are interested in it and want to see how it behaves. And this is the central notion of the thesis. So so to complete the definition, we need to add one more thing. This is not well defined in the sense that there could be no such minimum k. So let's take the class of stars, for example. So a star is, every graph of this form, right? So it's k1m, let's say m, where m ranges over the naturals or something. So all bipartite cliques of one vertex on one side. And technically this is not a minor closed class, but let's forget about that for a second. And is there any k? What's the delta of this class? Let's say it is 5 or something. But this cannot be the case, because this would mean that every star is a minor of another star of maximum degree 5. But the only way to include a star as a minor is with a bigger star, right? Like a star of maximum degree 5, or k for any constant k, has at most 5 vertices. We can't even get bigger stars. We can't get more vertices by contraction. So we can't get bigger stars by contraction. And the bigger star has a bigger degree. So there is no such k. In this case, we set delta of C to be infinite. And we have a bunch of classes for which we have found this value. So as I told you, for form K5 it is 3. So we do have that delta of form K5 is 3. Now there are other cases. For what about delta of form K3,3? The the class of forbidden bipartite graph of 3 vertices on each side. It is 4 in this case. So we also have a non-trivial lower bound. Yes, we can get, and in fact we can get every possible value. So delta, the class of 3 with less or equal than k, has delta exactly k for each k. So this is nice, that it's, this would match precisely. And if I have time, I will show how we get, the lower bounds, that it cannot be lower than k because it's not obvious. Actually, I can show like a very simple lower bound. So for form K3,3, it's quite simple really. We want to show that not every graph in form K3,3 is a minor of another graph in form K3,3 of maximum degree 3. So let there be G in form K3,3 which includes K5 as a minor. So you might recall that by Kuratowski's theorem, this is basic graph theory, every planar graph, a graph is planar if and only if it excludes K3,3 and K5. So in other words, I'm telling you this is a non-planar graph of form K3,3. So it can be proved that in this case, this graph has maximum degree 4 or higher, right? And then we ask ourselves, can we find another graph G prime that includes it as a minor and has maximum degree 3? Well, it cannot be a planar graph because a minor of a planar graph is planar. So it has to be again a graph in form K3,3 which includes K5. But in this case, it also has maximum degree 4 or more. And so this gets us a simple lower bound. And let's show at least one proof for this presentation. One, not instant proof. So let's show this guy that delta for K5 is 3. And by the way, let's address the cases where delta of say is 2 or 1. Well, what does this mean? It means that every graph in C, if delta of C is 2, let's say, then every graph in C is a minor of a graph with maximum degree 2. But what are those graphs? They're just, paths, cycles, maybe there are some isolated vertices, and this is their disjoint union. And that's all those graphs could possibly be. And in fact, every minor of such graphs is also of this form. So a class of delta of say 2, let alone 1, is quite trivial, and we don't bother with such classes, and we assume from now on that all classes don't have this value. So in this sense, 3 is the best we could hope for, and it's an instant lower bound as well. So delta of form K5 is 3. And how do we go about this? So there is a structural theorem by Wagner from 1930 something. It says that every graph in form K5 can be expressed, can be constructed by the clique sum of planar graphs and the Wagner graph. That's an if and only if statement. And I will explain what a clique sum is. But W8, it's just some specific graph. It doesn't matter. You just, take a cycle of 8 vertices and then you connect opposite vertices. Doesn't matter. And by a clique sum, we mean that. So let's take two graphs. Let this be G1. So the clique, this is a graph operation, this is its symbol. And this is another graph, G2. And we just identify their vertices. So in some manner of our choosing, in some one-to-one manner of our choosing. So we identify this to this, and this to this, and this to this. Say. So we get. Maybe I should have started with the image. So this is pretty obvious, right? And actually. Not any clique sum, 0, 1, 2 and 3 clique sums, which by a 3 clique sum I mean a clique sum using triangles, like this. Clique sums are always done with same sized cliques. So those are 2 cliques of size 3. And the same, a 2 clique sum is a clique sum with cliques of size 2. Which is basically, edges. The 0 clique sum is just the disjoint union, which means adding the graphs together and not identifying anything. And also, as part of the operation, we also have the right to remove a few edges from the clique. Just because we can. We have that right. And we will use this theorem to prove that delta of form K5 is 3. And I'm showing this just because I want you to see at least one proof to get a notion of how we think in these cases. And how might we do it? And the answer is, so we want to show that for every graph in form K5, we can find some graph in form K5, including it as a minor with maximum degree 3. And the trick is to take its planar decomposition into clique sums. So let there be G in form K5, and let G1, G2, and etc. until Jn or something be the graph used in Wagner's theorem to construct it by clique sums. And the trick is for each of those planar graphs, we pull the same trick as we pulled before. And the hope is that, they will all have low maximum degree. So the hope is that then we will find some way to clique sum them so that we get G as a minor again. And everything will have low maximum degree. And maybe I will not show it exactly for 3, but maybe I will show it for some low value, maybe 5, 6. And you will believe me that with some changes we can do it in general. So let's say G1 is, let's draw this a bit bigger. And again, this is G1. And it's starting to get a bit messy, so I will delete some stuff soon. And okay, so let's do what we did before with planar graphs. So let's, take and actually let's draw a second graph. So again, turning vertices of degree more than 3 into circles. I think that's what we wanted to state. And you will notice that our main problem is that we kind of can no longer do clique sums, right? Because we no longer have triangles. Like, we could do two sums still, and those are easy to deal with, so I will just focus on three sums, and the rest is similar. So what do we do about this? So here is how we approach it. We will go here and add a triangle. Right? And this is still a planar graph, right? So we have the right to do that. And when we go to, we still do the same inflation, but we don't inflate the red triangle. So we will, so an extra guy will appear here. And the good news is that we can click some on this red triangle now, right? And in fact, you will notice that so we again, to get the original graph G1, we contract the circle. Now it's one part of the triangle as well, and so on with the other two circles. And you will notice that this trio of circles will become a triangle again, and since we will have click-summed what G2, let's say, on this triangle, after the contractions it will be click-summed on the original triangle that the trio of circles represents. And so this is good news. We do this for all other triangles as well. And now I didn't mention this. The reason we can add a triangle here and still be planar is that those triangles will be empty. Must have an empty interior. And the reason for that is that or an empty exterior, one of the two. Because if they have something in the interior and in the exterior, then we can further decompose it into the clicks. We could further decompose C1 into the click-sum of smaller graphs. Basically, this triangle and what is inside and would be the one graph, and this triangle and what is outside would be the other graph. So let's say at least the interior or exterior must be empty, and let's say it's the interior, and we have this idea. And the good news is now we only need to care about the red triangles. All other vertices will have maximum degree 3. And now the problem is those could still have unbounded degree, right? Because let's say we let's say we click-summed 1,000 graphs on this triangle and could get arbitrarily large for arbitrary graphs. Then the triangle would have a degree 1,000 possibly, right? So the way we deal with this is, notice this guy is planar. Like you just append one triangle into another, and therefore it is K5 minor 3. Therefore, we can click sum it to this graph, J1 prime, let's call it. And this graph would remain K5 minor 3. So, sure enough, that's what we do. And when the second click sum comes on this triangle, we can give it over to the second triangle, and then we can add a third triangle, and so on. Right? So, and so each triangle gets at most one click sum, and each vertex of a triangle has like, if we forget the clicks, about the click sum, like degree 4 or something like that. And now you know, we will still get the original graph back with the right kinds of contractions. We need only, you know, we contract upwards. Those vertices and those vertices and those vertices. And so, and then we do this contraction as well. And we do get a triangle back again. And everything will be click summed on this triangle in the end. And you should be able to believe me. Now, we do this for every GI. So you know, we will click someone here a triangle which is also produced, generally speaking, in this procedure. So it will also have maximum degree about 4. So you should be able to believe me that we can get a graph that has maximum degree 7 or something. And with some tweaking around, we can reduce this down to 3. So this is the proof that delta of 4k5 is equal to 3. And now we would like to explore the structure of delta. So, you know, maybe it is an increasing function, right? Intuitively speaking, this sounds like it could be potentially correct, right? Yeah. By the way, let me mention first in short. So it's nice to show how our results tie to the literature. Markov and C in 2009 proved that delta of TW less than or equal to K is more than 3 for graphs of a very large number of vertices, something like more than 1,000 or 20 or 20 something. So we have extended this a bit by showing that it's larger than or equal to K, and also there needs not to be any restriction on the vertices. And also our proof is a bit similar. So is delta of C increasing? So this would mean that if C is a subclass of C prime, then delta of C is less than or equal to delta C prime. And this is not the case. So why? So we know that the class of stars, and I told you that let's forget that they are not minor closed. The reason is that, you know, just take their minor closure and you're fine. Like it's almost the same class. It just has some like pointless extra isolated vertices, so it doesn't matter. We can as well pretend that it's the same. So stars is in the class of planar graphs, which is in the class of apex graphs. So a graph is apex if and only if it is planar or it becomes planar after the removal of a single vertex. So, but this guy has delta infinite, this guy has delta 3, and this guy has again delta infinite, right? And the way you see that apex graphs have delta infinite is that, well, every pyramid is an apex graph, right? So a pyramid is like an n times n grid. An n pyramid is an n times n grid. So all those guys are vertices right here, and this is like the 1, 2, 3, 4, 5, the 5 times 6 grid. We also add an extra vertex that is connected to everything. And that's the 5 times 6 pyramid or something, a pyramid. So the point is that, let's say that every apex graph is a minor of another apex graph with maximum degree k. Then the reason this cannot be the case is that, you know, let you know, those be the connected components that stand for the vertices. And stuff. Sure enough, we can contract those vertices because and the graph will remain apex, because apex graphs are minor closed, like every class we deal with in this lecture. Yeah, and the problem right now is, if this graph is apex, well, what's the apex vertex? We needed to delete a single vertex and get a planar graph. But if this grid is very large, and we have to be able to include even very large grids, because we need to be able to include all grids with an apex graph of maximum degree k, then let's say that you know, this is the apex vertex. Well, at most k edges going to the grid will be lost, right? So if we have a large enough grid, we will be able to find some grid which has lost, for which the inflation of this vertex, call it V, here, will retain all its edges, right? So, because we could delete at most k edges, but a large enough grid with a vertex going to it, with a vertex, extra vertex connected to everything, this couldn't be planar. And so, like, this would be a part of, you know. And maybe, yeah, we can contract this guy as well into a single vertex. And the reason it couldn't be planar is because, well, there are many ways to see it. You can find the K5 minor in it, you can use Jordan's curve theorem. So, this doesn't hold. And, okay, we might say, okay, what about relaxation at least? So let's say that we would like, at the very least, to have the following. At the very least, we would like that for every minor closed class C, okay, there exists a minor closed, a proper minor closed class C prime, and proper means it doesn't include all graphs. I will get into that. So that includes C, and delta of C prime is finite. So basically that's a conjecture. So yeah, if it isn't clear, everything that I've mentioned so far and hasn't had someone else's name, we have proved during this work. And similarly, the conjecture, etc. are ours. So it is my joint master thesis work with Angelos Georgakopoulos. So the reason we take this to be proper is, well, because if it isn't proper, this is a pointless question, because, well, the class of all graphs has delta 3, right? Because, well, take any graph, just for any vertex with degree more than 3, just split the vertex into many vertices, have them be so that they all have maximum degree 3, and connect them in some way, and this will still belong, the graph we will get from that will have maximum degree 3 and will belong to the class of all graphs. And this looks like it should hold, right? So surely, like, there must be some class including C and not having delta of C infinite, right? And from now on, we assume all classes are proper as well as minor closed, and we have this result. Which is a nice result, right? And it is kind of unexpected. And this has a few corollaries, right? So So for K6, the class of graphs excluding a K6 minor, it contains all apex graphs, right? So this means that it has delta infinite, a class usually very hard to work with. And in fact, the same holds for Kn for all n greater or equal to 6. Also, delta of form K n comma n for the same reason is also plus infinite for n greater than 4. The linklessly embeddable graphs, those are a well-known 3D analog to planar graphs. You would think that we may find some trick with them like we found with planar graphs. But they also include all apex graphs. So similarly, they have delta infinite. So it's nice to find such general results. And let's tie this a bit to known results and see how it connects. And let's get into our major contributions. Or rather contribution. So the conjecture doesn't hold. And we hopefully all know the graph minor structure theorem. It was reached to after 30 years of work by Robertson. It was brought by Seymour and Robertson after 30 years of work, 500 pages of papers, 20 or so papers. It was completely seminal. MMA got allow us to pray to him rather than to Robertson and Seymour rather than him, and it says that every minor closed class can be characterized by a list of excluded minors, which is finite, and I won't get into that. Now another result they proved, so that was the graph minor theorem. Another result they proved is the graph structure theorem. And what the graph structure theorem says basically is, remember how with Wagner's theorem we had that and let's write that again, if we had a bigger board, but we don't, we wouldn't have erased it. So remember how Wagner's theorem said that every graph in form K is in form K5 in the if and only if it can be constructed by the clique sums of planar graphs and W weight. Well, Robertson and Seymour said, look, it would be very nice if we could prove this for some class excluding some arbitrary minor, right? So for arbitrary rates. Let's say, and that's what they proved, see, is in 4 bands. Then, and we only have the one side. We don't really have a good structure for arbitrary rates. J is constructible by the clique sums of the so-called K almost embeddable graphs. Right? And so which is some class of graphs that I might get into if I have enough time. And in 2016, Dvorak and Thomas proved an alternative, a variation of this theorem. So this theorem has many variations. So let's say if H is not arbitrary and is more specific, let's say it is in a planar graph, we are able to say, more specific things about what we can, by the clique sum of what graphs we can construct it with. So, like that's in 2016 by Dvorak and Thomas. Okay, for H that is not arbitrary but is apex. Then, sure enough, and I think that's Ethan Olive. And here we have like the class of so-called strongly K almost embeddable graphs. And using this result, and gathering others, Morin, Wood and Dudjmovic, I hope I pronounced it right, proved a bunch of characterizations for the classes of graphs that exclude an apex graph. So, it's like Wood and Morin and Dudjmovic. They prove that the following are equivalent. Okay, for proper minor closed class set. Okay, sure enough, C excludes an apex graph as a minor. Every graph in C can be constructed by the clique sum of strongly K almost embeddable graphs. I will not write it. And there are, I think, 3 other conditions, like, every graph in C having bounded layer tree width, like layer tree width less or equal to K. for some k constant, etc. By the way, I didn't say this. Here, k is a constant that depends on h. And yeah, they had this theorem, and they proved what they wanted to prove. So, you know, this was something, and this was something, and this was something. A proper minor closed class C excludes an apex graph if and only if it has a proper minor closed superclass of delta 3. So that's a new result. And so that's nice. And it's not at all obvious why this would be the case, right? Like, the other day I tried this with degeneracy instead of delta. So, you know, you define the delta of set, you could define the deads, the degeneracy of set, or the LTW, the layer 3 width of set. You just take the same definition and